Okay, in this video, we're going to talk just quickly about reversing the order of integration when you're using polar coordinates. We did that when we were using Cartesian coordinates. You should be able to write a double integral for area either as a dy dx double integral or a dx dy double integral. That's a skill you should definitely know. On the previous video with polar coordinates, we set up all of our integrals in the orientation r dr d theta, and never discussed how would you set it up if you reverse the order of integration, which in theory should be able to be done. And what I want to show you is, generally speaking, it's not always advisable to write the integral with the limits reversed. In other words, doing d theta and then dr. But I'll show you what it looks like, because occasionally you might be asked to do this. Let's first talk about the common orientation with polar coordinates, which is dr first and then d theta. So we're going to describe this region, this right triangle, in terms of polar coordinates. So here's the way to think about this. Is another way to think about orientation, and this works for rectangular coordinates as well. If you take the last variable, what you would want to be thinking about is, for a given value of theta, for an arbitrary value of theta, remember theta equals 0 is facing the x-axis, and as theta rotates counterclockwise, r would be the distance from the origin, and so theta clearly would go from 0 to this angle y equals x is pi over 4, right? That's 45 degrees. So for an arbitrary theta, what would r vary from? That's what we want to think about. So for an arbitrary theta, r goes from something to something else. So if you pick a random theta somewhere between 0 and pi over 4, so let's say right here, this angle theta, what does r vary from? Well, the minute you move away from the origin, you're in the region. So my smallest value for r would be 0. And when do we exit the region is when we hit this line x equals 1. And remember, in polar coordinates, x is r cosine theta. So that would be the same as r equals 1 over cosine theta, or r equals secant theta. So r goes from 0 to r equals secant theta. And you can see that's true no matter what my angle theta is, right? If I pick any theta in this region, I'm going to always go from 0 until I hit this line, which we now know is r equals secant theta. So putting limits on this integral, r goes from 0 to secant theta, and theta varies from 0 to pi over 4. So that would be how you would set up the integral in the normal, usual note orientation, which is dr first and then d theta. But how would I describe this same region if I reverse the order of integration? So we want to do this as d theta first, and then, and then r second. So what we want to consider now is, for an arbitrary r, so think about distances from the origin. A certain distance from the origin would fall on sort of a part of a circle, right? Because all these points are the same distance from the origin. So if you consider arbitrary r values right in here, what does theta vary from for any of these arbitrary distances from the origin? Well, theta goes from 0 to pi over 4. So for a given, another name for arbitrary is just a given or a random. For a given r, theta varies from 0 to pi over 4. But is that always true? So I was going to continue this picture. If I continue this, you might see that once I get to right here, I'm going to draw this last one right here. That's part of a circle. If I go further, then an R value, further, this distance wouldn't go all the way to 0, right? It would definitely go to pi over 4. So I need to draw these in blue here. These theta values for given values of R go from pi over 4 as a maximum to this line right here. So they don't go all the way to 0. So we have to separate this into two separate integrals. So for this value, right, let's go back to this one. For these values of R, for given R, what does R vary from? R goes from 0, and of course this distance is 1. For given R such that R is between 0 and 1, then theta is going to vary from 0 to pi over 4. But now let's see if we can go straight to this. R greater than 1, but less than or equal to, what would be the maximum value for R? This distance, right? Remember, this is a 1 by 1. If you did the Pythagorean theorem, this hypotenuse has a length of √2. So from R equals 1, that would be this length right here, that would be 1 unit of length, to this length here is √2. That means R is between 1 and √2. Theta varies from, so I could write that just as an inequality as well. My maximum value of theta here is pi over 4. But my minimum value goes to the line x equals 1. And remember, from the previous one, we know x equals 1 corresponds to R cosine theta equals 1. But I need a bound for this in terms of theta. So I'm going to isolate cosine theta is 1 over R, which means theta itself is the inverse cosine of 1 over R. So that's my lower bound. That's x equals 1. If you solve it for theta, is the inverse cosine of 1 over R. So the bottom line is, because theta's bounds are different depending on what R is, we're going to need two integrals. We need two double integrals to describe this area. So the first one's going to go, and remember, we're doing this as, the R can still stay out in front, but we're doing d theta dr. From this value, we saw that if R varies from 0 to 1, theta will go from 0 to pi over 4. But for this upper half, not even half, a little less than half, R d theta dr, as long as my R is between 1 and √2, theta is going to vary between the inverse cosine of 1 over R to pi over 4. So both of those integrals together describe that right triangle. And so one thing you see from this, it is definitely, in most cases, easier to integrate, go back to the top one, to describe a region in polar coordinates as dr first and then d theta. Things get a little more complicated when you reverse the order. But that's what it looks like.